So now that we've considered all the types of bonding, we're going to look at how the bonding affects the physical properties. And physical properties are things like melting and boiling and condensing and freezing, conductivity, and then their solubility. So how easy is it to separate the particles in the lattice? How easy is it for the substance to conduct charge? So does it have a free charge carrier? And how well does it dissolve, and in what type of thing? To do that, what you need to do is consider the structure and bonding present. So when a question asks you to consider the structure, it wants you to tell the examiner whether you believe the substance is giant metallic, so made of metal atoms only, giant ionic, a metal bonded to a non-metal like sodium oxide or potassium chloride, or is it only containing non-metals and therefore covalent? And there are two types of covalent structure: macromolecular, carbon as diamond or graphite, silicon or silicon dioxide. There are macromolecular substances. So we have carbon, silicon, and silicon dioxide. So carbon being diamond, graphite and graphene, silicon being silicon, and silicon dioxide, SiO2. They're the macromolecules. If it's made of any other non-metals joined to non-metals, then it's simple molecular. That would be things like carbon dioxide, methane, iodine, water, just two non-metals joined together. And we're going to talk about the lattice structure, the bonding. So we're going to say water is simple molecular with covalent bonds between the atoms, but to separate one water molecule from another, we overcome weak intermolecular forces, and we might have to decide which type, and we would consider that from the previous things we've studied. So if we go back and we have a look, this first bit, what we need to consider in each type of bonding is changing state. So in year 7, you probably drew a diagram of a solid all nicely lined up and a liquid with the particles a bit further apart and a gas with them able to move freely. Energy is needed to complete these processes to change because we need to overcome whatever forces hold the particles together. If you look back at the flow chart, if I scroll down, it's the forces holding the particles together here. We need to work out how much energy we need to overcome these. If this says strong, then we are going to need a lot of energy. Whereas if this says weak, we're not going to need very much. So it's going to be easier to change states. So how much energy is needed to change the substance from a solid to a liquid to a gas? So we might want to say that energy is needed to overcome the forces, and when we get to each type of bonding, we'll discuss the types of forces holding the particles together. The stronger the forces, so if they say that they're strong, the more energy is needed. Which means the higher the melting or boiling point. What about conductivity? Well, something can conduct if there are charged particles that are free to move. And so we have two types of things that can conduct, that can be free to move. We've either got delocalized electrons, and we find those in metals or graphite, or we've got free ions in ionic substances that have been molten or dissolved because the ions become free. Those things will conduct electricity. So we'll find that we've got this ability to conduct. Solubility depends on the ability of the substance, the solute, and the solvent, the thing that you're trying to dissolve it in, to attract one another. So if we're ionic, so we have pluses and minuses, or we're polar, delta pluses and delta minuses, then we're going to dissolve in polar solvents because we like them, such as water. If we are non-polar, then we'll dissolve in non-polar solvents, things like hexane. Maybe cyclohexane, hexene, anything that's non-polar. In the next few videos, we will look at each type of bonding and structure independently.